Okay, yeah, it's a great pleasure to be a part of this session. ADSC certainly changed my life, and I'm grateful to many people from whom I learned a lot of stuff. Many of them are here, some of them are not here. So just to preempt, one question is, where did you get this T-shirt? I didn't make it myself. It's actually available on sale at ICTP gift shop. And I was there recently and couldn't resist buying a dozen or so T-shirts. Okay, so yeah, so my talk will be have some overlap with Juan's, but it will be different. I thought just for younger people to recreate the spirit of 20 years ago, it was really a phase transition that took place. It took place between strings 1997 and strings 1998. And actually, if you look exactly June 30th, 1997. I remember that period well. It was right after the Amsterdam Strings Conference, which was highly successful. There were, at that time, there was essentially a small group of people working on something called D-brain black hole or D-brain black brain correspondence, which was the aftermath of Polchinski's D-brain paper. And basically, the idea was to stack lots of brains on top of each other and compare them with the metrics with the same macroscopic charges that they produce. And this is more or less actually the subject of my talk in strings 97, was to study the case of n D3 brains on top of each other. It was clear that there was something particularly nice about D3 brains as well as M2 and M5 brains, that the metric that they create is completely non-singular. And the metric actually differs from ADS5 crosses 5 by this extra 1. So in the spirit of it's not a thing of the past, actually this touches on David Kutasov's talk just now, because what this 1 does is it introduces an irrelevant operator, which is a lot like T mu nu squared. And I spent quite a while worrying about the effect of this extra 1. So if you look at schematically, you have these D brains on top of each other with open strings, and a asymptotically flat space due to 1, which goes into this throat. And the throat is, of course, ADS5 crosses 5. The throat is at small r. Okay, and then when you can, so I still actually think that it's somewhat useful to keep this asymptotically flat space and 1 in the metric for some purposes. For example, if you match the macroscopic brain tensions, you get this relation between 't Hooft coupling and the radius of space. And then it's basically, so the crucial thing is, in addition to the usual 't Hooft large N limit, which suppresses quantum corrections, there is the real crux of the sort of ADS-CFT revolution was this new dramatic simplification for large 't Hooft coupling, so the metric has small curvature. And then you can make various simple calculations, like the Bekenstein-Hawking entropy of the near extreme brain, and it agrees up to some factor of 3/4 with weakly coupled Super-Yang-Mills theory, or you can compute low energy absorption cross-sections, and it turns out that secretly this actually computes normalized 2-point functions. For example, the dilaton corresponds to trace F mu nu squared. And in this computation, it actually was important that there is this extra 1, because the asymptotically flat region helped you normalize the vertex operator. So these were the type of things that gave hints for some kind of agreement between gravity and gauge theory. Okay, so then, of course, the ADS-CFT came out of Juan's paper, where the low energy limit was taken directly in the geometry. And in some sense, you forgot this 1. So it amounts to forgetting this 1. And now 20 years later, some of us are trying to remember this 1. It kind of goes in circles. There were several attempts to remember this 1. part of the interest is that if you flow all the way back to the UV, you can get asymptotically flat space. So who knows, maybe this T mu nu square type deformation could still, we could learn something about it. This is a picture of ADSC FT tiled with cows, just to remind us that the whole thing is still a bit of a spherical cow, right? It's a rather, so back then, I thought about it as a kind of rather special limit, a toy model for extremely strongly coupled, highly symmetric gauge theory, where the serendipitous simplification happens of weak curvature, so it allows us to solve strongly coupled gauge theories. Then, of course, the range of the whole thing has expanded dramatically. We no longer think about this as a sort of rather special thing. We think about holography. Okay, so David instructed us to try to come up with 3 lessons learned. Of course, there are many lessons, but one thing seems to me very interesting is that string theory can make definite testable predictions, at least about strongly coupled gauge theory. For example, already back in 98, it was predicted from this formula. Here, you take so when you look at massive string states, this quantity is very large, so the whole thing is of order ml, and you get this formula, lambda to the 1/4, you get times some square root of the excitation level for the massive string, is a firm prediction. And amazingly enough, it has been verified using integrability. So Pedro Vieira mentioned this in his talk. He was one of the originators of this. So it's really possible to not only compute planar perturbation series to very high order, but also to extrapolate it. And now people have compared not just even this lambda to the 1/4, but all sorts of subleading terms. So it's really a beautiful curve that matches. And there were similar successes for the dimension of high spin operators, which are dual to spinning strings. So you can say that these are not experimental tests, but nevertheless firm tests of string theory. So string theory really comes out of gauge theory at this very strong coupling. The other lesson is color confinement. This is where my colleague Sasha Polyakov had some early ideas. Actually, at that strings 97, he talked about the idea of warping, and that it could somehow help get confining strings. And then in the context of gauge gravity duality, it basically comes realized that basically in ADS space, this radial coordinate just goes out forever, but in a confining background space ends. And this has been a source of a semi-infinite number of papers of hard wall QCD, ADS QCD. One can just chop off at some Z maximum and find, and as long as A squared of Z maximum is non-zero, you find that this string that lies down here is a confining QCD flux tube. And this doesn't have to happen by just chopping it off by hand. It can happen dynamically. Ideally, what you want is that this happens through dimensional transmutation. And Matt Strassler and I found an example of this where there is logarithmic flow at far in the UV, and then this transmutes into the scale of confinement. But this actually still happens to be a rather special example. And the dream back then very much was to find the string dual of an asymptotically free gauge theory. I think some of us were somehow optimistic then, but this is one thing that actually has not come realized, and I think this is a really good problem to return to. I mean, the essential difficulty is that, of course, the Hopf coupling becomes weak far in the UV, and you cannot use this nice supergravity approximation. But still, we have sort of the right tools, I think. So it would be really great to return to the problem of confinement. Whenever I talk to people who are not specialists on this and I tell them, would tell them, like, I see a dimensional transmutation, and then they would be very puzzled, what's happening? So in this theory, there is logarithmic flow, but there are two gauge groups that flow in opposite directions while staying strongly coupled. So it's still a rather special supersymmetric thing, and if you want to give up supersymmetry, you really have to face asymptotic freedom. Lesson 3, see the word hole? I didn't see Juan's slides, but it still appears here. I think it's fair to say that this is, the whole thing has become way more than I or anyone else could have expected, not just 20 years ago, but even 18 years ago. There has been an amazing range of physical applications. So in addition to strongly coupled plasmas and many body physics, we have learned a lot about quantum entanglement through the Ruta-Kayanagi and HRT formula, quantum information, and this is teaching us, and also, of course, the thermofield double. That was sort of the original thing due to Juan about eternal black hole and thermofield double. So this is teaching us a lot about the mysteries of black holes and quantum gravity. We have also learned a great deal about Chern-Simons matter CFTs, both in this ABJM example, which is a dual to ADS4 cross S7, and also there are higher spin ADS CFTs, which somewhat unexpectedly have had applications to real world boson-fermion equivalences that we heard a lot about at this conference, in particular at Shiraz-Minwala's talk and Nati's talk. Okay, a brief wish list, that's also David's instruction. So obviously something that we really wanted to do back then and still want to do is getting some sort of better control over the much more generic regime of couplings which are not much greater than 1 but are of order 1. Most gauge theories, non-supersymmetric ones, cannot penetrate to this extreme large lambda regime but just sort of settle. You have to settle in this regime. Often nature lives in this maximally complicated regime. So I think we have no choice but to face it, and I think this is where the higher spin versions of ADS-CFT can still come in very handy because they keep track of the higher spin operators and so on. Now, we often talk about ADS-CFT as giving us insight on quantum gravity, but realistically speaking, we've done little about quantum gravity effects. They're encoded in 1/n corrections, and we're just starting to scratch the surface there. I think there is lots of room for improvement, and this is something Juan already mentioned, CFT's dual to de Sitter space cosmology that would be really much closer to real world. And then I have a final wish that is partly inspired by the excellent coffee breaks and partly by my recent work, which is more melons. Yeah, the quality of melons at the breaks was quite exquisite. And then, of course, we heard there is a mini revolution, the malonic revolution, which is a new type of large N limit where only malonic diagrams dominate. It's not quite as simple as these vector models, but it's still a very simple model. It turns out that this is a way to get SYK-like dynamics without disorder, as was pointed out by Edward Witten. Just actually on Halloween day, the paper appeared and made me drop everything and start learning this stuff. So here are pictures of these melon diagrams. You see a couple of melons. And there are models where you can represent them as triply colored sort of stranded graphs. They're a bit similar to matrix models, but unexpectedly they're simpler. So that's basically all I had to say. So I look forward to, wow, it now looks like ADS-CFT is all set for, I don't dare to make predictions for how many more years, but I think when that famous conference in Santa Barbara where basically every speaker would go to the podium and say, oops, I changed my title. I'm going to talk about something related to ADS-CFT. So even then, I think people thought, well, that's a hot topic for a couple of years. But no one was thinking 20 years, so I don't dare to make predictions. Thank you.